We will later on learn how to manipulate wide sensor stationary processes in LTI systems and so on in the next chapter. However, in this chapter, I wanted to have one example. And in this example, let's x of t be a wide sensor stationary process and s of t to be an integral of x of t over an interval. So I consider an interval of, let's say this is time t, and I get here t plus cap t, and then this is t minus cap t, and this is like your random process, and the area underneath of this function, which is this area, I calculated. So I want to know that if x of t is WSS, and if s is equal to this integral, I want to calculate properties of s of t, or cross correlation of s of t and x of t. In this example, we want to first calculate mean of s of t. Obviously, s of t is an integral, so this is equal to integral of expected value of an integral. Remember that expected value itself is an integral over the distribution, and these two integrals, the boundaries of the integral, they are not a function of each other, so you can change the order of the integral. So you could put expected value inside the integral, and then you get this. So expected value of x of alpha, because you said that x of t is wide sensor stationary, expect value of this is constant, so you get mu x of which is not a function of time, and then you have to integrate it from t minus cap t to t plus cap t alpha. Now, the integral of a constant function is equal to the upper value minus lower value times mu x, which is 2t times mu x. Now, we want to also calculate S of, let's say, t plus 2 and t. Okay, we don't know if it is wide sensor station or not, but we'll prove that it is. So if I calculate this expected value, this guy, using the definition we have, this guy is equal to this integral, and this guy is equal to this integral. I used two different dummy variables. I kept alpha for the first one, and so here I replace this t by t plus 2, because here I have t plus 2, okay, for this one. So t plus 2 needs to be substituted by this t here. And this is why I get this one, and I use the same dummy variable. But for the second one, I just replaced the dummy variable alpha by beta, which I could, because I want to merge these two integrals. So I will have expected value of double integral, and then I could put the expected value inside the double integral. So I will have the outer integrals. These two guys becomes the outer integral, and this expectation goes inside. I get this. So now these guy, because I know that x is WSS, this is equal to Rx at time alpha and beta, and because this is WSS is only a function of time difference, becomes Rx of alpha minus beta. I make abbreviation, I don't need to put comma 0. So now this integral is over this area, and this example is very important. I want you to pay attention and look at this graph very carefully. So first of all, I'm integrating over two dummy variables. One is alpha and the other one is beta. So let's say beta starts from t minus, so suppose that this is t, and then I have to get t minus cap t and t plus cap t. And beta starts alpha starts at time, let's say this is time t plus 2, and then interval of t plus 2 minus cap t, and then t plus 2 plus cap t. So what we are doing is we are integrating over this rectangle. So inside this rectangle, I will color it with blue. So inside this rectangle, so this corner, the coordinates of this corner, the alpha is equal to t plus 2 plus cap t, and the beta value is t plus cap t, and this corner is t plus 2 minus cap t, and the beta coordinate is t minus cap t, and so on. Okay, and then you integrate it over this area. The thing is that this function is a function of alpha minus beta. So this double integral could be simplified if we change these two dummy variables of alpha and beta. So this pair of dummy variables, I want to change it to something such that I could convert the dummy, the two double integral into a single integral. So to do that, I define nu equal to alpha minus beta plus 2 and gamma equal to alpha plus beta. From here, if I calculate this one, so we see that d alpha d beta is equal to so it's kind of like you have a Jacobian, and also you need to change these boundaries. So if you want to stay in the new coordinates, so let's say here is new direction and this is gamma. So on this point, you can calculate, on this corner, you can calculate the value of nu and the value of gamma. On this corner also, you can calculate value of nu and gamma, and same thing for this one, and so on. And then you have lines on this new coordinate, the new with the 2D plane of nu and gamma instead of the 2D plane of alpha and beta. And then use these lines and then do the integral. So I want you to do this in details. So if you do that, this double integral could be written over this. So it's like you rotate this 2D plane 45 degree or so, and then you have what you can do, you can easily prove that this double integral could be simplified, because and it's gonna be like that. So because this function of yours here is constant over any line parallel to gamma axis, because this becomes gamma and this becomes constant with respect to the gamma variable. So it comes out of the integral, and then it becomes length of this line times the r of gamma. Length of this line, and length of this line is equal to this function. So this is the length, and so on. So the integral will be simplified, and you can easily show that this is a convolution of that. So what happens is that the if you give this random process to this integrator, so the autocorrelation function of the output is equal to the convolution of RXX autocorrelation function of the input with this rectangular pulse, which has a width of let's say here is 2t and minus 2t.